Hi everyone, I am here to discuss time complexity. Time complexity is very important topic that every computer science student must be familiar with. Not only computer science student, those who aspire to get an IT job in a service-based company or a product-based company must be familiar with this concept. So those who do competitive coding, I need not tell, they work more on time complexity and coming out with efficient algorithms. I need not tell about the competitive coders. Hmm, then, so what is time complexity? Time complexity measures the amount of time needed to run an algorithm. Amount of time needed to run an algorithm. This amount of time can be measured in any computational unit such as seconds, minutes, or milliseconds, microseconds, nanoseconds, etc. Then the time complexity is always described as a function of n. What is n here? N is nothing but input size. That means size of the elements on which some algorithm is going to be performed. Then it is estimated that the time complexity is estimated by counting the number of elementary operations performed by an algorithm. Elementary operations. What are elementary operations? For example, let us assume there is one statement in the algorithm like a equal to a plus 1. This can be one elementary operation. Let me take another one, a equal to a multiplied by 2. This could be another elementary operation. For the sake of convenience, we assume that all the elementary operations, irrespective of their nature, they consume equal amount of time. Equal amount of time. We assume that they consume equal amount of time. Then, so we will be counting such elementary operations and that could become the total time complexity of an algorithm. Then what sort of algorithmic steps may be there or what sort of steps may be there in an algorithm? The steps in an algorithm could be sequential steps, loop statements, and function calls. The measurement of time will vary for sequential steps, loop statements, and function calls. So these three are the possible steps in an algorithm. Then, before going into the details, what is the first? Let us realize what is the purpose of time complexity. So, time complexity is used for performance analysis of algorithms. Why do we need to do this performance analysis? Again, the purpose is twofold. Very first one, to assess the computational resources. To assess the amount of computational resources required. And the next purpose is to compare between different methods and choose the best one. And choose the best one. So what could be the best one which consumes lesser time complexity will be the best one. So this is the purpose of time complexity. Along with time complexity, there is one more characteristic which is used or which is involved in performance analysis of algorithms. That is nothing but space complexity. In this video, I am not focusing on space complexity as the length of this video may become very large. So I am postponing this discussion of space complexity, and I will do this as a separate video. Okay, so next, let us focus on asymptotic notations that are used to describe time complexity. So asymptotic notation. In mathematics, asymptotic notation is, or asymptotic analysis is used to describe the nature of limiting function. Here we are going to use asymptotic notations to describe time complexity. There are 5 asymptotic notations. I have mentioned the first 3 over here, and remaining 2 I will tell what are those later. So first, big O notation. Big O notation. How to understand this big O notation? Let us assume the time complexity of one algorithm is mentioned as big O of n. The meaning of this is n is the upper bound. Upper bound. That means the algorithm cannot take time beyond or more than n. Can't go beyond n. That is called upper bound. If I mention big O of n is the time complexity of one algorithm, the maximum amount of time that the algorithm takes is n, not more than that. Then another notation is big omega notation. If I mention the time complexity of one algorithm is big omega of n, it is called lower bound. The meaning of this is the algorithm cannot take the time complexity below n. Can't go below n. This is the meaning of big omega of n. Another asymptotic notation used is theta of n. This is called tight bound. Theta is called tight bound, which is a mix of upper bound as well as lower bound. The meaning of this is, if we mention any algorithm's time complexity as theta of n, then the time complexity of that algorithm is very closer to or almost closer to n. So that is the meaning of this theta notation. Along with these 3, there are other 2 notations which we may not use very much. They are like small o, small omega. Out of all these 5 notations possible, the very commonly used asymptotic notation is big O notation. So we will be using only big O notation. For a beginner, this is enough. Those who study design and analysis of algorithms as a full-time course, they can focus on the remaining notations also. But I am considering only big O notation in the examples that I am going to discuss further. Next, what are the different types of time complexities? So I told you that I am going to consider a big O notation. Big O notation. I have considered 8 different types of time complexities here: constant time, logarithmic time, linear time, logarithmic time, quadratic time, cubic time, exponential time, and factorial time. I have considered 8 different types of time complexities possible. There are some more actually. These are enough to discuss. Next, first one, constant time complexity. How this constant time complexity is represented? It is represented as big O of 1. Logarithmic time complexity. It is represented as big O of log n. until and unless I mention explicitly, it is to be understood like the logarithm to the n is to the base 2 in computer science. Next, linear time. This is represented as big O of n. Logarithmic time. This is represented as big O of n log n. Some people call this as linear log time also. Or sorry, log linear time. Next, quadratic time. Quadratic time is nothing but big O of n square. Cubic time is nothing but big O of n cube. Exponential time is nothing but big O of 2 power n. Sometimes we may also get some time complexities like 3 power n, etc. These are also called exponential time complexities. Next, the last kind of time complexity is big O of n factorial. This is factorial time. So these are the different types of time complexities possible for the problems. When it comes to the order of growth, I have arranged all these time complexities in the order, in ascending order. In ascending order. That means constant time complexity is lesser than all. Next comes logarithmic time complexity. Next comes linear time complexity. Next is log linear, etc. The 8 time complexities that I have considered here are arranged in the ascending order of their growth. You can understand that constant time is best, the best time complexity. Next best is logarithmic. Next best is linear. Next best is n log n, etc. The most dangerous time complexities are big O of n square, n cube, 2 power n. All these are dangerous. Especially the exponential time complexity and factorial time complexity are the most dangerous time complexities. Next, let us see what is meant by constant time, and let us discuss in detail about this one. As I told earlier, constant time is measured like it is represented as big O of 1. Constant time is nothing but it is independent of n. Constant time is independent of n. Let me take one example quickly. If a greater than b, big equal to a, else big equal to b. Let us assume the statement is given like this. Is it depending on any input size? No. So for these kind of statements, the time complexity is big O of 1. Big O of 1 does not mean that it takes only 1 unit of time. It is to tell that it takes constant amount of time. It does not depend on external inputs. It does not depend on external input size. Let me give another example. For I equal to 1, I less than or equal to 10, I plus plus. Print hello. How many times does this loop statement executes? It executes for 10 times. It prints hello for 10 times. Is it depending on any n or any external input? No. It is not depending on it. So that's why we can say, though it is a loop statement, we can say that it consumes big O of n, big O of 1 time complexity. Next. Another example, or I can take for this constant time complexity, are operations performed on stacks and queues. They consume constant time complexity. What are the operations we can perform on stacks and queues? We can perform insertion, deletion, finding the topmost element, etc. in stacks, insertion and deletion in queues. For these kind of operations, they take constant time complexity. That means they don't depend on those operations. Time complexity will not depend on the number of elements stored in stack, number of elements stored in queue, etc. So these are also good examples for constant time complexity. The other two examples I have given. Next one, logarithmic time complexity. Logarithmic time complexity is represented as big O of log n. Let me give one example. For I equal to 1, I less than or equal to n, I equal to I multiplied by 2. Let me consider n equal to 20. Print hello. Now let us assess how many number of times this hello will be printed if the loop executes. Let us try to find it out. When I equal to 1, it prints hello. I is less than or equal to n. Okay. Next time I becomes 2, it prints hello. Next time I becomes double its previous value, it prints hello. Next time I becomes 8, it prints hello. Next time I becomes 16, it prints hello. Next time I becomes 32 and it cannot satisfy the condition I less than or equal to n, it fails, it can't print. So totally how many number of times this hello got printed? 5 times. How to measure this value 5? This can be done in a simple manner. Let me take this as we need to find this 5. How we got this 5? So let us work out like this. I need to find how many number of times this loop is getting executed. Let us call that as x. So 2 power x less than or equal to n. The logic here is when 2 power x is less than or equal to n, it is getting printed. Next, to resolve this relation, let me take logarithm on both sides. If I take logarithm both sides, then this will become log 2 less than or equal to log n. Next, if I take x on the left hand side and send this log to the right hand side, it becomes log n to the base 2. Log n by log 2 and 2 becomes base of this one. So if we represent this with big O notation, this could be represented like log n to the base 2. So how many number of times this loop is getting executed? Big O of log n to the base 2. This is one good example for logarithmic time. Then any other examples I can take. One important example for this logarithmic time is binary search. Binary search is an efficient efficient search method which consumes log n to the base 2 time complexity. So the idea behind this binary search is the whole array whose size is n will be divided into exactly 2 halves. Then the search operation is performed either in the first half or in the second half. That means the size of this sublist becomes n by 2. Next, again the same process is repeated, the division happens. Next, the size of the list becomes n by 4 and so on until the size of the list becomes 1. This division happens. So here it consumes, that's why it consumes big O of log n to the base 2 time complexity. Okay. Next, let us discuss linear time. Linear time is measured as big O of, linear time is represented as big O of n. For example, if input size is 10, how many number of operations it will perform? 10 operations. That is called linear. Let me take one example. For I equal to 1, I less than or equal to n, I plus plus. Print hello. How many number of times this loop statement executes or prints hello? That is nothing but n times. So this time complexity is measured as big O of n. Okay. The best examples for this linear time complexity are linear search operation. Linear search is nothing but finding whether an element is present in the given array or not. Finding sum of natural numbers, n natural numbers, finding max, min, etc. in array, in the given array. These are all max or min in a given array. These are all good examples for linear time complexity. So finding sum of natural numbers you can do with the help of a for statement. There is one direct formula available which is nothing but sum equal to n into n plus 1 by 2. So using this formula, we can find the sum of n natural numbers. Suppose if you are applying this formula, please remember that the time complexity is constant. This finding sum of natural numbers can be done in two ways. One is using loop statement and another one is applying direct formula. If you are applying direct formula, the time complexity is constant. Why? Because it does not depend on n. N could be any number. The number of operations will not vary. Okay. That is about linear time complexity. Next, linear arithmetic or log linear time. So it is represented as big O of n log n. It is represented as big O of n log n time complexity. So one example I can take for this is for I equal to 1, I less than or equal to n, I plus plus. For j equal to 1, j less than or equal to n, j equal to j multiplied by 2. Print hello. Printf hello. What is the amount of time complexity taken by this segment of code? It is a nested for statement. The outer for loop, I loop, runs for n times. The inner loop, this I have also discussed as an example for logarithmic time complexity. The inner loop executes for log n times. So on the whole, the time complexity is n log n to the base 2 time complexity. This is one example for log linear or linear arithmetic time. Other examples we can take are sorting techniques, efficient sorting techniques, merge sort, quick sort, heap sort, These will consume big O of n log n to the base 2 time complexity. These are good examples for this log linear time complexity. Next one, quadratic time complexity. Quadratic time complexity is simple to understand. Big O of n square. For example, if the case is like for I equal to 1, I less than or equal to n, I plus plus. For j equal to 1, j less than or equal to n, j plus plus. Printf hello. Can you please tell me how many number of times this will be printed? Outer loop n times, inner loop n times. That means when I equal to 1, j takes the values 1, 2, 3, 4 and so on up to n. That means for every I value, j will be completely executed. 1, 2, 3, 4 and so on n. So I goes up to n and j goes up to n every time. So totally big O of n square time complexity. One example I can give is matrix addition. Takes quadratic time. Another example is consolidated multiplication table. Consolidated multiplication table can be printed like this. Printer %3d, comma, I multiplied by j. After j loop, print one empty print state, empty line, printf \n. That's all. This code will print consolidated multiplication table. So this will also take big O of n square time. Next, cubic time. Cubic time is big O of n cube. One example I can take is for I equal to 1, I less than or equal to n, I plus plus. For j equal to 1, j less than or equal to n, j plus plus. For k equal to 1, k less than or equal to n, k plus plus. Print high. So can you please tell me how many number of times this high will be printed onto the screen when n equal to 2? It is 8 times. How does it print when I equal to 1, j equal to 1, k can take one value, one time printed. I equal to 1, j equal to 1, k can take value 2, two times printed. I equal to 1, j equal to 2, k equal to 1, one time. I equal to 1, j equal to 2, k equal to 2. And other possibilities are I equal to 2, j equal to 1, k equal to 1. I equal to 2, j equal to 2, k equal to 2. I equal to 2, j equal to 1, j equal to 1 already covered. Sorry. J equal to 2, k equal to 1. I equal to 2, j equal to 1, k equal to 2. I equal to 2, j equal to 2, k equal to 2. So totally how many number of possibilities are there? 8 times this high message will be printed. This is nothing but big O of n cube time complexity. Some examples I can take are matrix multiplication. Matrix multiplication is one good example for this cubic time complexity. So when the time complexity is cubic, we must find some optimizing measures to bring that down to linear complexity or quadratic time complexity. Next one, exponential time complexity. Exponential time complexity is big O of 2 power n. So this is quite dangerous time complexity. The big O of 2 power n time complexity can be arised in the cases like generating subsets or power set generation, generating power set generation for a given set. This consumes 2 power n time complexity. Another example I can take is recursive function to find nth Fibonacci number. These are the two examples where we may get big O of 2 power n time complexity. Next time complexity is factorial time complexity. Factorial time complexity is big O of n factorial. It is represented like this, where we get this kind of situations. One example is permutations generation. Permutation generation for a given set. Here the time complexity will become big O of n factorial, and another possibility is traveling salesman problem. There are some problems which are called NP complete problems in design and analysis of algorithms course. They will be having the time complexity big O of n factorial. Traveling salesman problem. No one wants to write a solution in big O of 2 power n or n factorial time complexity, but some problems need the solution to be written in those complexities. Why? Because there would be no alternative for them. So these two are good examples for factorial time complexity. Here I have come up with some exercises to just revise the concepts that we have covered so far. I have come up with 10 exercises. Let us quickly go through them. This is the code given to find the factorial of a number. Find the factorial of a number. So this is an assignment statement which takes big O of 1 time complexity, big O of 1, big O of 1, and this is a for statement. So how many number of times it is this for loop is getting executed? Big O of n. So totally on the whole, the time complexity of this code is big O of n. Next one. A equal to 0, B equal to 0, I equal to 0. So you can quickly tell how many number of times this loop is getting executed, big O of n times. And this is like big O of m. The whole program's time complexity can be mentioned as big O of n plus. Next one. This is a nested for statement. This is outer for loop. This is the inner for loop. You just check how many number of times outer for loop executes, n times. Inner for loop also executes by n, for n times. So on the whole, what is the time complexity? Big O of n square. Next, exercise 4. I equal to 1, I less than or equal to n. For, this executes for n times. This executes for log n times. Outer loop for n times, inner loop for log n times. Totally big O of n log n. This is the time complexity. Next, exercise 5. So this is same as our logarithmic time complexity. How many number of times this is getting done? It is like our binary search. Every time the I value is becoming half. Suppose if you take n equal to 20, in next iteration, this I will become, first I will be 20, next it becomes 10, next it becomes 5, next it becomes 2, next it becomes 1, next it becomes 0, and there it stops. So how many number of times it is doing? 5 times. This kind of example I have explained in logarithmic time complexity. The time complexity of this exercise is big O of log n. Okay. Next, exercise 6. Yeah. This is also like a logarithmic time complexity. I equal to 0 n times. Every time I is updated by k times multiplied by k. So this is nothing but big O of log n to the base k. If it is becoming double or half, we will write logarithm to the base 2. As it is multiplied by k times, we write in place of 2, we write log n to the base k. Next one. So this is an example for printing consolidated multiplication table. Which we have discussed already. So what is the time complexity of this? Big O of n square. Next one. Next exercise. So I equal to 0, I less than 4. Would you say linear time complexity? No. It is constant time complexity. It is not depending on n. Next, exercise 9. This is also constant time complexity. Why? Because it is not depending on input size. It is square sum function which is performing a square, b square, c square separately and then summing up. So this is also an example for constant time complexity. Next one, exercise 10. So you see how many times this for loop is getting executed, n times here, n times here, and internally n times. This is nothing but the algorithm for matrix multiplication. The time complexity is big O of n cube. So these are the exercises I have considered. So to make you understand the analysis of time complexity in a much better way. I hope you understood the concept in a clear manner. So if you have any doubt, you pause the video and have a look again. So I hope you liked the video. If you have liked the video, please share it among your friends and subscribe. Thank you.